Sound is a very interesting wave because it's one that we encounter all the time. And as we've already talked about, sound is a longitudinal wave. So I have a longitudinal wave drawn here. And so we understand that with sound, we still have our wavelength from our compression to our compression. So this area here is still going to be our wavelength. That doesn't really change. In fact, the wave equation still holds true for the velocity of a sound wave. So v equals frequency times the wavelength. We'll talk about this a little later on. Before we do that, I wanted to talk to you about how sound is actually created. Sound requires a medium that has a molecular structure because sound creates vibrations, and the vibrations actually will create some different pressures within the medium itself. So if we're talking about air, what happens with sound is if you ever look at a speaker actually moves back and forth and back and forth, and what that does is that actually moves the air molecules and it creates different air pressures. So we have higher air pressure and we have lower air pressure because the air particles, they're going to move back and forth because it is a longitudinal wave. So we have these areas here of our compression, and this is where we have our high air pressure or high pressure. So in that area, that's where the air molecules are combined together. They're actually closer together. So we have higher pressure. Over here, this is actually our lower pressure. So this is low pressure. And this is where the air molecules are farther apart. This is actually called a rarefaction. So a rarefaction is where you have the molecules spread out. So it's kind of like your crest and your trough in a sense, although it's not really called a crest and a trough because we're dealing with a longitudinal wave. We have our compression with high pressure. We have a rarefaction with the low pressure. So the sound is going to travel through this medium. The air molecules are just going to move back and forth and create the higher pressure and the lower pressure areas. And so that's why you see the speaker actually moving back and forth, and that's how that actually occurs. Now, sound actually will travel at a set speed, just like our other waves in a set medium travel at a set speed. So if you're talking about the speed of sound in different materials, that's not going to change. You can have a higher frequency sound, a lower frequency sound, but the velocity is still going to remain the same. In fact, just a few known things. If we're talking about air at 0 degrees Celsius, we have a speed of sound of 331.5 meters per second. If we're talking about air at 20 degrees Celsius, we have 343.5 meters per second. In water, the speed of sound is different. That's why sometimes if you're talking underwater, you sound a lot different than you would in air. And that's about 1,480 meters per second. In fact, it doesn't just have to be air or water. Other materials as well, like lead. You can actually have sound travel through lead. It's a different speed. It's about 1,200 meters per second through lead, but we do have an actual speed of sound. The sound wave will travel through lead because it has a molecular structure. The other one that's very interesting is human tissue. Now, sound can travel through human tissue. In fact, it's called ultrasound. So when you actually have an ultrasound done, that's just sound waves that are traveling through human tissue, and it travels at about 1,540 meters per second. So you notice that the sound will travel at different rates through different media, and that's just like any wave that we have. The important thing that I want you to get out of this is if you look at air, because air is really what we're going to be dealing with most often, you will have different speeds of sound based off of different temperatures of air. And that's because, as you know from your gases travel, the molecules of gases travel at different speeds in different temperatures. When you have a gas that's heated up, that has a higher temperature, the air molecules are going to be more excited. They're going to move around a lot more freely than if you have a gas of lower temperature. And so because of that, lower temperature air will have different and lower speeds of sound than higher temperature air. In fact, it's important to understand that the speed of sound of air is really derived from this formula. It's 331.5 meters let's just say degrees Celsius, not meters per second, 331.5 degrees Celsius plus 0.6 times T, where T is the temperature in degrees Celsius of the air that you're looking at. So if you were to plug in 20 degrees Celsius in here, that's how you get 343.5. And I'm going to be giving you problems where you're going to have to figure out what the speed of sound is in the air based off of the temperature of the air. Now the other thing I want to talk about is with the wave itself. Now, when you're talking about sound waves, there are a couple of terms that you hear. One is pitch, the other one is loudness. And a lot of people have a tendency to get these kind of mixed up. So I want you to understand that the pitch deals directly with the frequency of the sound. The higher the frequency, the higher the pitch. The lower the frequency, the lower the pitch. So pitch is just another term for the frequency of sound. Loudness has nothing to do with our velocity equation. It has nothing to do with the velocity, the frequency, or the wavelength. The loudness comes directly from the amplitude of our wave. The greater the amplitude, the greater the loudness. The lower the amplitude, the lower the loudness. So we can change the loudness of the sound without actually changing our waveform itself. Now, sound is also interesting, and you're going to see as we progress through the sound unit, because you can create different standing waves of sound waves. So just like we were looking at standing waves on a spring or on a string, you can actually create sound waves that are standing waves as well. In fact, that's how different musical instruments are created. So as we go through, we're going to be looking at really 3 cases where you can be able to create sound waves as a standing wave. So we're going to be talking about a standing wave on a string again, and the reason why that's important, if you think about a piano or a guitar or any type of a string instrument, sound waves are actually being created by a standing wave on the string. We're also going to be looking at open pipes, and we're going to be looking at closed pipes. So flutes are an example of an open pipe. Closed pipe is actually going to be a clarinet. So we have different instruments that are being created by sound waves, just creating standing waves inside these different instruments. So sound is very interesting, and it's really an important part of our life because we're able to hear it all the time. So just understand that it's a wave, just like any other wave that we've looked at. So the wave velocity equation works. It does have a fixed velocity, just like any other wave as well.